All right, so we're going to run through some limit laws today in this section. And so this is kind of exciting. These laws that we're studying on this guy right here will follow us throughout the rest of the book. And when we get into derivatives, which I don't know what a derivative is, cool, doesn't matter. A derivative is a limit. So all the derivative rules later on, they're just limit rules, or laws if you prefer. And then later on we get into integrals. Second semester, it's an integral. Again, it doesn't matter right now, but I'll tell you this, it's a limit. So all the laws for integrals are just limit laws. So if you hammer these today, you're gooch. So if you have the limit of f of x plus the limit of g of x, obviously both as they approach a, what that means is this. I can simply take the limit of f plus g of x like thus. In other words, I can treat them as one. I can treat them as one formula, or I can do them separately. What do you mean, Grim? For instance, x squared plus 2x plus 5. I see three functions right there. So if I say to you the limit as x approaches 2 of this mess, you're like, but Grim, isn't x squared plus 2x plus 5, isn't that a polynomial? It is. Aren't polynomials continuous everywhere? By God, you're right. But go with me for a minute. What this says is I can do each of these pieces individually, thusly. And then we're going to actually do some other cool things with this in just a minute as well, but not right the second. So as approaches 2x, plus the limit as x approaches 2 of 5. I'm going to start with the easy one. What is the limit of 5? What is, in other words, what does 5 approach as x approaches 2? Listen, bro, what part of a constant do you not understand, dog? This limit is 5. Does that make sense? It clearly has to be 5 because it doesn't change. What part of constant do you not grasp, sir? Now, this one here, you're like, dude, isn't it just 4? It is just 4. Wait, isn't this also just 4? Dog, it is. So the answer is simply 13. It's the limit of each of the individual pieces. Groom, is it true that the sum or difference of a limit is the limit of the sum or difference? That is correct, sir. That is correct. Well said. I couldn't have said it better myself. Darcy, thank you. That was awesome. Now, what about this one? The limit of k times x, where k is simply k is simply a what? It's a constant. What that can be done is this. We can pull that constant out front. We call that the linearity of limits. In other words, it's just factoring it out. So what is the limit as x approaches a of x? Well, the limit is a. And what about this k? Literally, it's just k times a, and you are done. It is that easy. Okay? That easy. Okay? But what if it wasn't just x? What if it was the limit as x approaches a of k times f of x? I know what you're thinking. Isn't it just k times the limit? You are right. But what is the limit? Well, in this case, I don't know. But as soon as I found the limit, let's say it was 11, it would just be 11 times whatever k is. That's it. That's it. What is k? K could be 2. Wait a minute. K could be 2. You mean like literally right here? Literally. I could have done this instead. 2 limit as x approaches 2 of x. Well, this is 2, and this is also 2. 2 times 2 is 4. Okay? Could have done it that way. Fact. We will use that quite a bit going forward. It's kind of a big friggin' deal. It's kind of a big friggin' deal. Now, what about this one? What if I have f of x times g of x? And what if I take the limit of that? The limit as x approaches a of this mess. Well, what is that? Well, it says that it's the limit as x approaches a of f of x times the limit as x approaches a of g of x. It's that easy. Give me an example. My God, I'd love to, sir. What if we did the limit as x approaches 0 of x e to the x? You're like, dude, that's easy. I know. So the limit as x approaches 0 of x times the limit as x approaches 0 of e to the x. Well, this is 1, this is 0. The answer must be 0. Okay? I know what you're thinking. Groom, is this a continuous function? That's an excellent question. And we, as I said, we talked about continuity a little bit today. But this is a combination of two functions. X, which is continuous where? Everywhere. E to the x, which is continuous where? Everywhere. And if I times them, guess what I get? Continuous where? Where? Everywhere. So literally, I could have just dropped the 0 in there, yes? And evaluated it. But that won't always be the case. For instance, this guy right here, check it out. Bloop. There's f of x. Here's g of x. Bloop. That's hot. Whatever. This is like, I don't know, 2. That's hot. So when I do this, f of x times g of x is going to be 2 times 2, which is going to be up here at 4, yes? Ta-da! What about this one, Groom? This is up here at 4. This one's down here at negative 2. That's cool. So 4 times negative 2 is going to be where? Negative 8. Done. Done. And we can actually graph that. And in fact, it's kind of cool to watch because if you pull up the Desmos.com, for context, that was a burp. In case you're weird, like what's his butt? That was also a burp. Oops. Whoops. Whoopsie poopsie. Dog. Check this out. X plus 5 is a perfectly good linear function. True dat, homie? 2 minus x is also a linear function. What? Shut up. No, I won't. Shut up. No, I won't. So check this out. When you do this, what happens at here? Well, at negative 5, it's negative 5 for the blue guy. And then at negative 5, we're at, I don't know, 7. Nice. So what is negative 7 times 0? Turns out it's 0. That's why the red guy has a 0 there. Yes? Sweet. What about negative 4? Well, negative 4 is 1, yes? And the green guy is 6. And what is 1 times 6? Last I checked, it's 6. That's why we're up there. What about this guy up here? This feller is at 12.25. No friggin' way. Where do those guys cross? They cross at 3.5. What is 3.5 times 3.5? Why, it's duh. It's, what is it? It's duh. It's 12.5. 12.25. Now, how about here? This is 0.10. This is 0.5. Yes. Oops. And this is 0.2. What is 2 times 5? It's 10. That's all we're saying here. Okay? And we're just saying you could put them together and create that red guy. That is the product. The limit of that product is the same as the limit of the blue guy times the limit of the green guy at any point in time. That's all that means. Always, always, always works. Okay? The quotient rule, of course, you're like, hey, I bet it works for division. I bet it does too, except what? F of x divided by g of x. What must be true? Now, some people would say that g of x can equal 0. That's not true. We say the limit as x approaches a of g of x cannot equal 0. So we say that this is the same as the limit of f of x over the limit of g of x. Okay? Ta-da! Not surprising even in the slightest. Even in the slightest. Okay? Now, what about this cat? If I take the limit as x approaches a of f of x squared. Groom, is it true that that's just going to be the limit as x approaches a of f of x squared? Yeah, in fact, it is. Wait a minute. Are you saying that if I had to find the limit as x approaches a of I don't know, 2x minus 7x squared plus 5x cubed squared, then I could literally just do the limit, as it approaches 3. the limit as x approaches 3 of 2x minus 7x squared plus 5x cubed squared. Well, yeah, and what about it? Well, isn't that the same as saying, now just watch Groom, watch him, 2 limit as x approaches 3 of x minus 7 limit as x approaches 3 of, wait for it, are you waiting? X squared plus 5 limit as x approaches 3 of x, cubed squared. Well, that's a lot of work, dude. It's not hard. So check this out. What's the limit as x as it approaches 3? Well, it's 3 times 2 is 6. Now, what about this cat? What is the limit as x approaches 3? It's 3. 3 squared is 9 times 7 is minus 63. The limit of x is, as x approaches 3, is 3. 3 cubed is 27 rather, and 27 times 5 is 135. And so if you plus those together, you get 135 minus 57. That's an 878, I think. Yes? And what is 78 squared? I don't know. If I had a calculator, I'd tell you. 78 square is 6,084, obviously. Duh. Okay? And that's how you would go about doing that. It just says you can move that exponent out there. I know what you're thinking. Groom, isn't it true that x to the 1/3 is the cube root of x? You are right. Whoa, hold up, bro. So you're saying that this exponent could also relate, literally that's what I said. So the limit as x approaches 3 of the cube root of 4 minus x is the same as the cube root of the limit of, as x approaches 3 of 4 minus x. Well, this limit is what? 4 minus 3 is 1. And what is the cube root of 1? The cube root of 1 is 1. Okay? That is the same thing. So technically, what your book writes is the limit as x approaches a of f of x to the, I think they use p over q, is the same as saying it's the limit as x approaches a of f of x, whatever that is, all to the p over q power. In other words, you like square it and then take the cube root of it, okay? Or just one or the other. Are you with me? It could be just one or the other. Not a big deal there, okay? Those are the limit laws. Now, we are going to spend some time on Wednesday doing some examples with these guys in a couple of different contexts, okay? A couple of different contexts. So we're going to look at them a little bit different. We're going to look at a little bit of graphing. We'll look at a little bit on our calculators, our Excel rather, and we'll do a few algebraically as well. Okay, so I just want to throw them out there for you today. That's in section 2.3. So you have enough to work on. I just wanted you to kind of get an eyeball on this before Wednesday when we do a little work day.